All right. Hello, everyone. I'm sure more people will be coming in momentarily, but it's good to go ahead and start on time. It is wonderful to have Fabian Ruehle of CERN and Oxford coming in today to tell us about learning Calabi-Yau metrics. He is going to present this from a broad view that should be accessible to people from all backgrounds. And it's based on work by him and Sven and some other people that I think a lot of us are really excited about, that there's this enormous problem that's been standing for decades in algebraic geometry and in string theory, that we have a theorem that guarantees the existence of appropriate metrics for doing string theory, but it's notoriously hard and not known in general how to construct them analytically. So he's going to tell us about how to machine learn those, and that is something that string theorists find very exciting, and I certainly do. So Fabian, please take it away. We're very excited for your talk. Thanks.
All right. Thank you very much. Thanks, Jim, for the introduction and for summarizing my talk. So indeed, I'll be talking about a paper that appeared recently together with Sven and collaborators from Virginia Tech. And it's also loosely based on previous work with Lafos and Lucas and very recent work with Anthony Ashmore. So the outline of my talk is the following. So I will begin with a brief motivation for why we're doing string theory. So why do we have this problem in the first place? Then I will briefly talk about metrics, because Calabi-Yau is a statement about metrics. And after that, I will explain what a Calabi-Yau manifold is, and finally, how we learn metrics for Calabi-Yau manifolds using machine learning. Good. So my motivation for string theory is the following. Most observations that we do in our universe can actually be explained with just 4 fundamental forces. So there's gravity, electromagnetism, and then 2 lesser known forces, which are the weak force and the strong force. The weak force sort of leads to radioactive decay, and the strong force keeps nuclei together. And that's all good and well. And we have theories that describe these 4 forces extremely well. For general relativity, we have, of course, or for gravity, we have Einstein's theory of general relativity. And for the others, we have quantum field theory or Young-Mills theory. So that's all good and well. But the problem is, if you try to combine these, you always get nonsensical answers. So you might say, well, okay, then don't combine them. Sure, that's a possibility, but if you want to ask questions about fundamental properties of our universe, then you need to study extreme situations. So for example, if you want to know what happened at the Big Bang or what is dark energy, you need to look at a theory where you have a combined framework to describe general relativity or gravity together with these other forces. Another example is if you want to study black holes. So what happens at the event horizon of a black hole? Or we're seeing hints that all particles and forces, in fact, come from some underlying grand unified theory. So they are, while an electron is different from a proton, there are hints that all these forces and all these particles actually are coming from some underlying grand unified theory. So we actually do need to combine them in some way, and this is where string theory enters. So string theory, the basic assumption of string theory is actually pretty simple. You're just assuming that the fundamental constituents of your particles and your forces are not point-like particles, but they are one-dimensional extended strings. So you take the point particle and you replace it by either a closed string or some open string that's suspended between 2 what's called branes. And this is the basic assumptions you do. This sounds pretty simple, but it does have far-reaching consequences. So one thing that follows from this is that you need to have 10 space-time dimensions. And of course, this sounds weird to you because last time I checked, the world was 3-dimensional. So what this means is we are only observing 3 dimensions, but the string requires 10. So the idea is that you assume that we live in this 3-dimensional space plus time, and the additional 6 dimensions that are required for consistency are somehow small and curled up and compact. And this is where the word compactification comes from. So we cannot see them. They avoid detection at particle colliders, for example, or just seeing them, but the string sort of lives in this 10-dimensional space-time and can see them and go through it, and both are happy. So now the problem with this is that you cannot just choose whatever you want for these compact dimensions. They have to have a very, very special geometry. And this geometry is what's called a Calabi-Yau manifold. And we will see in a short while why it's called Calabi-Yau manifold. Before we go there and talk about metrics and Calabi-Yau manifolds, I briefly want to explain how do we even describe these compact extra dimensions. And so just in general, whenever you want to describe some manifold or some compact space, it's usually easier to describe it as an embedding in some higher dimensional space. So think of, for example, describing a sphere. You could just take your normal R3 and you put an equation x squared plus y squared plus z squared equals r squared. That will define a sphere of radius r inside this real 3-dimensional space. Or if you take a complex projective 2-dimensional space and you write down an equation x cubed plus y cubed plus z cubed equals x, y, z times some parameter of psi here, this will describe a torus for you. So the way we will describe Calabi-Yau manifolds are precisely by going to some higher dimensional space called an ambient space, and then we describe the Calabi-Yau as some 6-dimensional object lying in this higher dimensional ambient space. But this is really just a trick we do to describe it conveniently. The space-time is fundamental 6-dimensional, or the extra space, the Calabi-Yau describes the 6th dimension. We're just sort of embedding it in some higher dimensional space to describe it conveniently. Good. So as I said, being Calabi-Yau is really a property of the metric of the space. So I will need to talk about metrics a little bit. The first thing to know about metrics is we can use them to measure distances, but this choice is not unique. So if you're, for example, in St. Peter's Square here in Rome, you might just sort of, and you are here and you want to walk to one of the pillars to see them, you can just sort of take the Euclidean metric or Euclidean distance, you can just walk here. If you're in Manhattan, unless you're a bird and you can fly, so it's not a good idea. You have to follow the block structure if you want to get to the Empire State Building. So you need some different type of metric also, or some different type of distance measure. So there, even though both are sort of in R2 or in R3, you can put different metrics here. And more generally, if your space is curved, the metric depends on the point you're at. So if you're here and you want to go here, you can sort of do what this guy is doing, although this doesn't look very safe. Or you could just walk around here. Whereas if you're sort of away from the half dome here, you can just walk directly from here to there. Also, it depends on the volume of your manifold. So this distance here is of course smaller than this distance, or the shape. This distance here is longer than this distance. Good. So when you have a metric, this really describes sort of how far away different points are. So you can use it to measure distance or volumes and so on. So in order to explain this, let's look at, for example, again, the sphere. Let's go to spherical coordinates. So instead of describing it as in terms of x, y, and z with x squared plus y squared plus c squared equals r squared, I'm just writing something that automatically lives on the sphere. So I'm going into coordinates where I have the radius and the angles theta and phi here. And then my metric will just be sort of diagonal, because I only have the r squared, the theta squared, and the phi squared, but no mixed terms. So this will be my metric. And then I can compute the volume by taking sort of the square root of the determinant of this metric and integrating this from r goes from 0 to r, and theta goes from 0 to pi, and phi goes from 0 to 2 pi. Good. So for the purpose of this talk, we want to think of metrics as being some map which takes in the position where you are in your space, the volume of your space, and the shape of your space, and maps this onto a d by d dimensional matrix. So for example, onto this 3 by 3 matrix in the case of a sphere or of a ball. And we will use a neural network to learn this function. So this is the basic idea. The input to the neural network will be the position, the volume, and the shape, and out comes the metric at this point. So now for Calabi-Yau spaces, as I said, these spaces need to be very special. They need to have a very special metric, and this metric needs to be in some sense flat enough. So if you have a metric on your Calabi-Yau manifold, and these metrics are not unique as we have seen, there's a condition that you can write down. It's just a complicated equation where you take derivative, where you take a metric, your inverse metric, and you take derivatives of this metric up to 2 derivatives. And this function here has to be 0. This is just what string theory tells. It is one of the consistency conditions. So whenever you have a space with such a metric, you have a Calabi-Yau manifold, and you can use it to describe the geometry of the universe we live in. Good. So of course, this equation looks very complicated, and it is now a very valid question of whether you can even find metrics that satisfy this. And the answer hasn't been known for a long time. And along came Calabi, and Calabi said the following. He said, if some topological conditions are satisfied, I conjecture that you can find a Ricci flat metric. I cannot prove that it exists, but I know it is unique. And 20-something years later, Yau said, well, I can prove that such a metric exists, but I can neither tell you what it looks like, nor do I know actually how to construct it. But Fields then said, okay, that's good enough for me. You get my medal anyways. So we have this theory by Calabi and Yau, which says that if you're given some topological conditions, which are actually pretty simple to check, you can construct metrics. You know something about the geometry of our 10-dimensional space-time. You know something about the geometry of the universe we live in, and it has a Ricci flat metric. If you didn't have this theory, it would be essentially hopeless to try to find a metric that satisfies this. That's all going well, but even now, 40 years later, we still don't know what these metrics look like. We know they exist, we know they are unique, but Yau's theorem doesn't tell us what they are, what they look like. So they have this this mysterious, elusive property to it, which has led to it featuring in different places in pop culture, for example, in video games, in music, in comics, in art. So you find them in many different places, and they always act as being this mysterious thing which you don't really have a good grasp or handle on. So what are these properties that Calabi said, these some topological conditions? Well, there are 3 of them, and I will explain what they mean in turn. So the first one is the manifold needs to be complex. The second is it needs to be scalar, and the third one is it needs to be Ricci flat. Good. So complex is I mean, we all know what complex numbers are. So when you now describe a manifold, let's say, for example, the sphere, then you typically cannot describe this just with one coordinate patch. But if you are an ice bear that lives on the North Pole and a penguin that lives on the South Pole, you can write down the part you see up to the equator, and the penguin writes down the southern hemisphere, and they overlap at the equator, and they can use this to describe this manifold, or this part of the manifold. And then when they meet and discuss, they can see the entire sphere. But of course, the penguin and the polar bear are free to make any choice about coordinate system they like, or any convention. They can use any convention that they like. However, at the overlap at the equator, where these overlap, of course, somehow these 2 descriptions have to be compatible. And if you have some complex manifold, this puts constraints on what your transition function looks like. So you have the coordinate system of the penguin and the coordinate system of the polar bear, and where they overlap, there has to be some way of transforming the penguin coordinate system into the polar bear coordinate system. The second property is that it has to be scalar, and this means that you can write the metric in terms of derivatives of a scalar real function called the scalar potential. So this means that I can choose a function k, I take two derivatives, and since my space is complex, I'm taking your complex derivatives with respect to z and the complex conjugate of z. And by doing this, I get a function in general. I mean, I just get some matrix, but if I choose my scalar potential correctly, this matrix will actually be a metric. So it will have the properties of metric, will be symmetric. This just means that k is smooth enough so it can be differentiated twice, and it has to be non-negative and so on. And from this, I can also construct what's known as the scalar form by just taking an anti-symmetric combination of the entries of the metric. So conversely, let's say you're given a metric and you want to know whether it came from a scalar potential, you would have to integrate it to undo these two differentiations. But this is, of course, very hard if you're just given this function to see which derivatives of which function produced it. To find the scalar potential is very hard. So instead, what you can do is you can take a derivative of this antisymmetric combination, and then since the derivatives commute, this has to be 0. So this is a way of checking that it actually came from some function k, even though you don't know what this function k was. But it's still simple to do. It's just taking a derivative. So the third property is it has to have Ricci tensor 0. So in general, what you can do is you just take the Ricci tensor. It involves two derivatives of the metric, as we had seen previously. The metric itself involves two derivatives of this function k. So you get some equation which has fourth order partial differential equation, and you can write this down, but this is very, very hard to solve. And sort of this is also not what Yau did in order to prove Calabi's conjecture. So what Yau did is use the following. You can write down these volume forms on these complex spaces, which we had seen before. So this, we can write down something which is just given by the square root of the determinant of the metric times dz1, dz2, dz3, dz1 bar, dz2 bar, dz3 bar. And since we have the scalar potential, we can form this scalar form here, and we can cube it, and then we precisely get such a volume form that we could integrate to get the volume of the Calabi-Yau manifold. So now on a Calabi-Yau, as it turns out, you can write down a second object, which is this omega here, which is the derivative of some function times dz1, dz2, dz3. So when I square this, I also get dz1, dz2, dz3, dz1 bar, dz2 bar, dz3 bar, like I got from J cubed. But of course, the volume of the manifold is unique up to a constant, which means that J cubed actually has to be equal to omega squared up to a constant. And this equation actually is much simpler to satisfy. It's still very hard, but it's simpler to do than this solving this fourth order differential equation. So these are sort of the things we have to check. We have to check the overlap. When we sort of go to different patches, we have to check that we can smoothly put it together to form a complex Calabi-Yau, a complex manifold. Then we have to check that it is scalar so that these derivatives vanish. And we have to check that it satisfies this equation here. Good, so let me now give the simplest example for a Calabi-Yau manifold. And that's actually a torus. This is a two-dimensional Calabi-Yau manifold, and of course, for this, we know the metric. So this is really a trivial example. The non-triviality comes from the fact that we need to do this in 6 dimensions rather than 2 dimensions. But it's still illustrative to do this in 2 dimensions first, and then sort of after that, I'll show you what to do in 6 dimensions. So what we do is we describe this torus inside some ambient space, as I said before. So as an ambient space, we take this complex projective space, which is a 2-dimensional space, which you can think of being this 3-dimensional space where we identify coordinates Z0, Z1, and Z2 with lambda z naught, lambda z1, and lambda z2, where lambda is some complex number. So this is in some sense taking C3 and making it compact. This has the advantage that this space is automatically complex, and in fact it is also Kähler. So mathematicians know that, or have figured out that you can write down a Kähler form or a Kähler potential, which is called a Fubini-Studi Kähler potential. It looks like this, and if you now take derivatives together, you get a well-defined metric on this MP2. That's good, because if we now describe the torus inside this surface, we are already inheriting the complexity and the Kähler property from this ambient space, which we chose to represent the torus in. So this already solves 2 of our problems. We only need to worry about finding the correct metric. And so you might wonder, okay, so why did I choose a torus? Why didn't I choose a sphere or anything other that lives inside the space? And the answer is that the topological condition which Calabi told you needs to be satisfied in order to find a Calabi-Yau manifold tells you the degree of the surface you need to write down. And this degree has to be 3 in this case. So you necessarily need to write down an equation that looks like this, and this equation just happens to be a torus. Put differently, a sphere is not a Calabi-Yau manifold, so you cannot find a Ricci flat. You can find a complex metric, a Kähler metric, but you cannot find a Ricci flat metric on a sphere. Good. So this is the 2-dimensional case. In the 6-dimensional case, you can do essentially the same thing. So we start with some equation of degree 5 inside P4. For example, this equation here is just some equation of degree 5. Of course, there are many more terms, but we chose to restrict to the simplest one, which has just this one parameter here, and this parameter parameterizes the shape of this manifold if you want. It's just some complex number. And again, sort of before we had P2 and the cubic equation, so now we have P4 and we take an equation of degree 5. And again, this ensures the topological property that Calabi told us we need to ensure in order to be able to find a Ricci flat metric in the first place. And the complex and the Kähler property is again just inherited from this P4. So we have again a Fubini-Studi metric on this P4, and we can use this to learn to write down a Kähler metric that's complex. Good. So let me now discuss how we go about finding or actually learning the metric, solving this optimization task of finding a function that is given of the shape of the manifold, the position of the manifold, the volume of the manifold, and gives us a Ricci flat complex Kähler metric. And so these are the steps that are involved. First of all, we need to find points that lie on this Calabi-Yau manifold. And then for each of these points, we optimize the function that is described by the neural network such that it satisfies the overlap, the Kähler, and the Ricci flatness condition. And then we just repeat this for different shapes and for different volumes. And this way, we learn a function that sort of depends on the points, the volumes, and the shapes, and gives us a metric or the Calabi-Yau metric at any point. So when it comes to sampling points, we have the problem that random sampling actually depends on the metric. So to illustrate this, take, for example, the disk, which is given by in R2 by x equals r cosine phi and y equals r sine phi. And let's say I just want to sample points on this disk. So one thing you can do is you can just sample uniformly from x and y with a flat prior. So you would just get something inside the square, and then you drop those which are not on the disk, and you get these uniformly distributed points on the disk. That's not good in our case because, well, in this case we're sampling sort of a one-dimensional or two-dimensional objects in a two-dimensional space. In the case of the Calabi-Yau, we are sampling a six-dimensional object in an eight-dimensional space. So you would never actually randomly produce a point that lies exactly on the Calabi-Yau. So another thing you can do is, of course, you can just sample from the sphere. So you say, okay, then I just write down coordinates of the disk where r is in 0, 1 and phi is in 0 to pi, and I'm just sampling uniformly in r and in phi. But then you produce a picture that looks like this, where you have much more points in the middle and much fewer points outside. So as it turns out, due to the way the metric is, you need to sample r squared inside 0, 1 and not r inside 0, 1. So if you sample r squared from 0 to 1, you actually produce this uniform sample. Whereas if you did the naive thing, you're doing it incorrectly. But in order to know what to use here, you need to know something about the measure or something about the metric. A third way of doing it is to use resampling. So sometimes you're sampling with the wrong one, but then you're assigning a weight to each of these points, and the weight sort of tells you how generic this point is. So if the point has many other points in its neighborhood, then it will have low weight, and if it has, if it's sort of uniformly distributed, so towards the outside, it will have a larger weight. So you can then use this to take your points and just redraw with a prior that is given by the weights that you determine for each of these points, and this will then produce this uniform distribution. Or you could just sort of compute these weights and use them in your, when you compute your loss functions with the neural network, you could just weight the losses for each point by these weights. But doing this sort of requires still doing the back propagation for each of these points. And essentially, so you would do this 100 times for the origin. So it's better to resample than to weight these, because the back propagation actually is very expensive in our case. And I'll explain in a minute why. But the better thing to do is to just use VO points here, because generating these points is very, very cheap. Good. So these are the techniques for sampling and resampling points. So how do we do it in our case? So the algorithm that works for Calabi-Yau is the following. You just sample points on a sphere that lives inside P4. And then you just find so I choose a random point here and a random point here. And I find the line that connects these 2 points. And then I intersect my line with the Calabi-Yau that lives inside this space. So in this case, it was described by polynomial of degree 5. So this will have 5 intersection points that lie on the Calabi-Yau by construction. And I just take these 5 points as 5 of the points that I'm optimizing my neural network later. And the weights can now be computed by just using this function omega, which we saw, and the Fubini-Studi metric, which is sort of the canonical metric to choose on P4. Of course, so if I knew the Calabi-Yau metric, I could do this directly, but I don't know directly the Calabi-Yau. I do not know the Calabi-Yau metric, but I can compute the weights using this expression. Then I can resample and just use a sort of a uniform distribution of points on my Calabi-Yau. Good. So now that we have the points, we set up our neural network. And the input to our neural network will be, as I said, the points on the Calabi-Yau. So these will be 5 complex coordinates or 10 inputs. The patch, which we evaluate the neural network, so being the North Pole or the South Pole patch. And we sort of choose an encoding where, in this case, you need not just 2 patches as for the sphere, but you need 5 patches, and we choose an encoding where a 1 indicates sort of the patch you are at. And then the point in complex structure, so in the deformation, so the shape, the point in the space, in the shape space you are at, which is also a complex number. This was just given by this psi here. So these are another 2 inputs. And the output will be just this complex matrix that describes the metric, and this turns out to be Hermitian. Yes, David?
Yeah. Do you know, do you know at the beginning that you need 5 patches?
Good. So you can find many different numbers of patches. So the canonical thing to do in P4 is, in P4 you have 5 coordinates, and each they cannot all be 0 simultaneously. That's not the point, because then this line would not be well defined. And a cover or a way of patching, of covering P4 is then setting. So if Z0 is not equal to 0, you set it to 1. You can use this lambda to just then, if Z0 is not equal to 0, use lambda is 1 over Z0. So you can set it to 1, and the others are just what they are. And this gives you, for each of them, you get one coordinate being set to 1, and this gives you a good cover. There are more. Thank you for the question.
I have a related question. So in this case, the generalization of David's question into more general toric ambience is going to just be related to combinatorics of triangulations or something like that. How do you have a sense of how hard it's going to get for more complicated Calabi-Yaus? Because you're starting with this very simple one with 5 patches, but in general you'll have many, many more patches.
Yes. So the thing that's not, the patches are not the problem here. The transition functions sort of never made any, they never acted up when we were training. Okay. And sort of just doing this for different patches wasn't the problem. The biggest problem is going to be the fact that I only wrote down 5 terms here, but in general you could write down 120 or 126 even.
To just be in the bulk of the moduli space.
Exactly. So in general you have 126 coordinates here, psi. And then when you want to learn this at a generic point for generic choice of these 126 parameters, you need to sample points from 126 dimensional cube in some sense, and then train at each point. And so either you have 126 computers to do this, or it's getting very, very slow. That's the biggest problem. Yeah, generalizing to more patches is not a big deal. Yeah, and the output will then just be this this complex matrix, which is Hermitian in this case. So it has sort of real eigenvalues in diagonal, and then 3 complex off-diagonal entries. So it's just 9 real degrees of freedom. So a way of saying this is we are learning a function from R to the 17 into R to the 9. And the whole name of the game now is to optimize the parameters of the neural network such that it's consistent at the transitions, it satisfies the Kähler property, and it is Ricci flat. And instead of Ricci flatness, we are ensuring that it satisfies this proportionality constraint J cubed equals omega squared. So we took a relatively simple neural network. We took 3 hidden layers with 100 nodes and a leaky reader activation function. And we also use the fact that there is already a good metric that's at least already complex and Kähler. It's not Ricci flat, but it's complex and Kähler, and this is the Fubini-Studi metric. So what we're doing is we start with the Fubini-Studi metric, and we're just learning a correction. So the neural network is not learning the Calabi-Yau metric from scratch, but it is learning how to correct the Fubini-Studi metric to be also Ricci flat. So we are already starting somewhat close to home, where 2 of the 3 properties are already satisfied, and then we're just learning the correction that makes this also satisfy the 3rd condition.
And you just do this via pre-training?
No, so you can compute the Fubini-Studi metric. This is very simple to just compute. So for each point, we just really compute this.
Yes. And
then we initialize our neural network. We take this thing here, and we initialize it with weight and.
I'm sorry, I misunderstood. You're measuring the fluctuations away from Fubini-Studi with the net.
Exactly. So the neural network is learning this correction to the Fubini study. And initially, its weights are essentially 0. So initially, the guess for the Calabi-Yau metric is just the Fubini study metric, but then we start optimizing it such that the overlap Tekela and this Morse pair equation are satisfied. So for the overlap condition.
Just going to say, so there could be Calabi-Yau metrics which are not connected to Fubini study in that way, I guess.
Yes. Okay. So first of all, I don't know whether there can be, but
yeah, okay.
it's a logical possibility. In this case, the G neural network would have to learn -1 plus G Calabi-Yau.
Oh, yeah. Okay.
Yeah.
Well, if you can't get it smoothly in that way, I mean, it could be that if it were the case that it wasn't connected to Fubini study, you could detect it using ML.
That's, yes.
It may be that the optimization simply fails for the cases that David's talking about.
Yeah. But of course, I mean, your neural network could learn this. So if it just learns sort of the inverse Fubini study times G Calabi-Yau, then this equation would also be satisfied.
Yeah, I guess I'm asking whether GNN has to be in some sense small. I mean, that's sort of my question.
It is a good question. It was, so for this parameterization, it was small for this particular case, but in general, I would know how to make a statement.
Yeah, fine.
I mean, so what we first tried was to, I mean, you might ask, why did I choose this multiplicative ansatz? I could have also just learned G Fubini study plus G neural network. And then we found that sort of G neural network was of the order of G Fubini study. And this can be large at some points. And neural networks don't like large output.
Yeah.
So that's why we chose this multiplicative ansatz, and this worked better.
Okay.
But I agree, you're right. In general, we don't know. But in this case, it worked, and maybe it has to work in general. I'm not sure that can make a statement whether or not they are connected to Fubini.
Working for a specific case is better than not working in general. So, I'm happy.
Yeah. And of course, Jim is also right. If we were to do this for other Calabi-Yaus, and we were finding that G neural network is learning something of the order of G Fubini study, is correcting it sort of at order 1, then this is, of course, not a sensible ansatz to do. Then you might just sort of learn it directly from scratch. And this might tell you that there's not a small correction in this sense. Good. So to ensure the overlap condition, we just compute the transition functions. That's also easily done. And then we're just sort of computing the metric in one patch, in another patch. So computed in the polar bear patch, computed in the penguin patch, and then use the transition function to go from the polar bear patch to the penguin patch and see that these two agree. So we're just doing this for each entry, and we're sort of taking then the L2 norm, squaring them all up, and do this for all points in our batch or in our mini batch. For Kähler, we just need to take the derivatives of this Kähler forms, derivatives of the metric essentially, which we can also do, and this will sort of again give you a bunch of, for each point you will get derivatives of GAB with respect to some other coordinate. And we just, again, square this and sum it up over all contributions. So at this point, this is actually by far the trickiest and slowest thing that we have to do, because we need to take derivatives of the neural network. We need to take derivatives of the metric. And we need to take these derivatives with respect to the input, not with respect to the variables. Of course, when you train it, you're always taking derivatives with respect to the variables. That's just what gradient descent is. But in this case, we need derivatives with respect to the input. And this is a bit iffy and was by far the slowest part. And the third one is really just this Morse pair equation. When you have your G, you can just take the determinant and you can compute omega squared and then just sort of enforce that they are equal by sort of taking this loss in terms of dividing. So if I take this equation, I divide it by omega squared. I set kappa to 1, and then I just take this loss. So we have these 3 losses, and when they're all 3, 0, I know that I have found the Calabi-Yau metric. In principle, of course, the way we should weigh these different losses against each other is not fixed. we found that sort of choosing lambda3 by a factor of 10 larger than lambda1 and lambda2, so choosing the more pair loss the largest works better. And this kind of makes sense because the way this is set up, we're already very close. We already satisfying overlap in Cal. We are not at the Ricci flat point yet. So weighting the Ricci flatness stronger in this case actually helped us in finding solutions faster. But in principle, you just perform a box search over these hyperparameters in the loss. Good. So that's what we did. We did several experiments. So first, we found that the results do not depend crucially on the neural network architecture or the activation function. We tried Ruehle, Tange, and Gilu. We trained the neural network with 50,000 points per complex structure for complex structure inside this box where I just choose the real imaginary part somewhere between -100 and 100. We used a fairly large batch size, just because we can. These points are very small. The neural network is not so large, so you're not running into any issues here. You can use a large batch size and an atom optimizer. We found that if we used more points, then actually the accuracy goes further up. So at this point, it's really just a function of us being patient and optimizing this for more points. Finding these points is, as I said, this is free. So this is something that's probably different from many applications in machine learning in, let's say, the real world. We can just generate our data and we can generate it exactly and we can generate it extremely fast. So finding points in Calabi-Yau is free compared to doing all these optimization tasks. We then use an evaluation set of 5,000 points. And we tried several methods to prevent overfitting. So we tried to train longer versus doing early stopping. We tried to include batch norm layers, dropout layers, and so on. But we found that none of this actually did improve our results. So we could just use the simple neural network, train for 20 epochs. After 20 epochs, we found that sort of the loss was not changing by a lot anymore, so we kept it there. So the only thing we could do to actually make it better was to use, let's say, 80,000 points or 100,000 points or whatever instead of these 50,000 points. I would imagine that eventually, if I was to compute 10 gazillion points, I would probably need a larger neural network. But at this point, sort of just adding points by keeping the architecture fixed helped us improve the accuracy. We implemented this in PyTorch and TensorFlow. And as I said in the beginning, we need to take derivatives of the neural network with respect to its input. And this is proved a bit tricky for us because in PyTorch, there are no backward hooks to do this actually for the input. And in TensorFlow, there's some weird bug which has to do when you have P4 and 2 gradient tapes. So if somebody knows a good way around this, I would be very curious to hear. So the problem in PyTorch is you need this extra for loop over the outputs. And this makes it slow. And here, this code actually just sort of goes into an experimental parallel for loop when you have these 2 gradient tapes and makes it just freezes the kernel. So this can be avoided by writing this somewhat differently. This one cannot be avoided and just makes it slow.
Are you going to talk about performance near the conifold point, or are you going to? Is this a good question to ask?
You can ask now, but it won't change the fact that I didn't prepare a slide on this. So there are special points in the moduli space. So when I choose this psi equals -5 in my conventions, your manifold becomes singular. So something special happens to the metric. But I just sample these randomly, these points. So of course, I'm not hitting the conifold point. I'm hitting points close to the conifold point. For example, this one, so psi equals -5. So somewhere these points are somewhere close to the conifold points. But these were the randomly sampled points I used. And of course, I wasn't hitting it spot on. And if you go a little bit away from the conifold point, your metric is already pretty smooth again. So it's a very narrow region where you manifold. So where you see the conifold imprinted. So in general, your loss, so what I'm plotting here is an interpolation of all of the metric at all of these computed for all of these points in the shape space. And you see that in some cases, so this is the Morse pair loss, this sigma which I had, so j cubed over omega squared, 1 minus j cubed over omega squared. You see that the larger I make the shape, the larger the error gets. But this can be brought further down by using better approximations. So here I just fixed now psi to be something 10, and I'm showing you the results for this fixed psi. So what I'm plotting is the Morgan pair loss, the Kerr loss, and the overlap loss. So this is, initially these are very small, and so these are arbitrary units, don't pay too much attention to the units, but they are much, so the Kerr loss and the overlap loss are much smaller because I'm starting close to Fubini studio where this is essentially satisfied. But the Morgan pair loss is very large because I haven't found the Ricci flat metric. The Fubini studio metric is not the Ricci flat metric. And then I start optimizing, and I can sort of push this loss down, which means in terms of more meaningful quantities, means that this deviation from the Morgan pair equation goes down by almost an order of magnitude, so from 40 or so, sorry, from 0.4 to 0.06 or so. So if the deviation was 40% at the beginning of training, it's 6% at the end of training. And if this was exactly 0, then you would have found the Fubini studio metric. Good, that's all I wanted to say. So let me conclude. We have used neural networks to learn moduli and position-dependent Calabi-Yau metrics by optimizing the underlying partial differential equations. And this is very important because it will tell us something about the geometry of the space-time we live in. In physics, we will need it to compute, for example, masses that appear in our particle physics models. We need it to compute properties of dark matter and dark energy. And it also has important applications in mathematics. And in fact, we don't need to stop here. In the paper, we also apply this to a generalization of Calabi-Yau manifolds, which are called SU3 structure manifolds. The ansatz we're using is completely generic. We're just optimizing sort of a bunch of conditions here. We're just making use of the fact that neural networks are universal approximators, so they can learn any functions, so in particular, they can learn the metric. And we are optimizing this function to satisfy the constraints that need to be satisfied by string theory. So we just have this continuous optimization task, which we use to learn the function that represents the metric on the space of interest. And then, yeah, you can do this for different spaces as well. Okay, thank you very much.
All right, thanks a lot, Fabian. That is a lot of fun to hear about. Beautiful work, and you know, the first step, and there were a couple groups that wrote papers at the same time, but the first step toward sort of systematically doing these things numerically in string theory and also in algebraic geometry, because mathematicians care about this apart from any string theoretic consideration. It was a lot of fun. Any questions for Fabian? Could you comment a little more on singularities, and as you approach points in the moduli space with singularities, how it affects how you think about things, and sampling of points, for instance?
Yes, good. So there are different types of singularities you could approach in the volume or the shape space, and different things happen to your manifolds. It could be that your Calabi-Yau itself just stays like it is, but some submanifold in there collapses. So your manifold itself stays finite, but some curve or some four-dimensional subspace in there collapses, or it could be that your entire space collapses and becomes singular. So depending on what happens there, of course, your metric will do different things. So if the entire space collapses, your metric will just have 0 eigenvalues. If a divisor, or if a four-dimensional submanifold collapses, your metric will look fine, but it will have sort of a sublocus where if you go onto this locus, your metric will be 0 there. But in overall, it will look okay. So one thing that should be said is when you do this sampling and you compute the weights, you make the parameters, this psi, if you make it very large, what you find is that this situation appears. So you're essentially sampling many, many points with a very, very small weight and a few points with very, very large weight. And if you just do this naively, of course, you're all of a sudden just optimizing the neural network on the same point over and over, and then you have this one point and you're multiplying the result there with 10 million. This is not a very good idea. So in this case, it becomes more important that you either do the resampling or use some other technique to ensure that you're not sort of taking just points from a very small region, your Calabi-Yau, and the very few ones that you have far outside there, you're just weighting with a ridiculous large number in the loss because this leads to numerical instabilities.
Excellent. Damian has a question.
Hey, Fabian. Very nice talk. I wanted to ask you, if you looked at the approximation function for this metric from the neural network, have you compared it to metrics at some degree for the polynomials using Donaldson's algorithm?
Yeah.
And how did it compare?
Yes, thank you for the question. I didn't talk about Donaldson at all because it would have required me to introduce a whole other set of machinery and another way of approximating Calabi-Yau metrics by approximating actually what's called a balanced metric. But so the neural networks, for a given degree, the neural networks are more precise than the Donaldson algorithm at the same degree. So this is due to the fact that you are actually comparing two different things. The Donaldson algorithm is producing also a special type of metric, which is known as a balanced metric, which satisfies a certain condition. But this is not the Ricci flatness condition. It's just a different type of metric. And of course, if you wanted, you could use a neural network to also learn this. But so the point is that in a specific limit, these two metrics agree. So if you take an infinite degree limit, then the Ricci flat metric is the balanced metric. And this is why you can use this other algorithm, take a limit and get an approximation for the Ricci flat metric. But in this case, we are optimizing directly the Monge-Ampere equation. So we are optimizing directly the thing that makes the metric a Calabi-Yau metric. So this is why there is no surprise that this is working better than using some other proxy that just in some specific limit happens to agree with the Calabi-Yau metric.
Okay, so I see basically what you're saying is that you cannot directly compare the sigma that you get for Donaldson with the sigma that you get for...
Yeah, I mean, you can compare directly, and we did, and the sigma in our case is much lower. I'm saying it's not a fair comparison because Donaldson is solving a different problem. Nowhere when you optimize Donaldson, when you optimize the Donaldson algorithm, nowhere is the Monge-Ampere equation entering. So this metric doesn't even know what you're looking for in some sense, whereas we are optimized directly to solve the Monge-Ampere equation.
Okay, but you cannot give an estimate of which K is actually the one that approximates, well, that looks closer to this approximation, let's say.
So in this case, we didn't have the parameter K, we were just learning the function directly. What we also did is we were using the Donaldson or an ansatz for the Kähler potential up to a certain degree K, and then we were optimizing this to find a Ricci flat metric, and this can be compared to using Donaldson's algorithm with the same Kähler potential. And then our results were an order of magnitude better.
Okay, thank you.
Donaldson. But yeah, so this is not a failure of Donaldson. So if Donaldson's algorithm is also working as good as it can, it's just computing a different metric. You're just abusing Donaldson to do something that it's not set out to do. Because Donaldson is giving you the correct metric. It is giving you the correct the correct balanced metric. It's just the balanced metric, not the Ricci flat metric that it's giving you.
Okay.
David.
Did you look at the metrics on the way, meaning that are not Calabi-Yau? And in particular, I mean, I guess what I'm in the back of my head, I'm wondering, would it look something like Ricci flow?
Yes, it's an excellent question. I don't know. So in particular, as I said, computing the derivatives are already a little bit iffy, and we just need to do this for the the J, so for the Kähler form. If you want to compute the Ricci tensor, you need to take more derivatives. You need to take two more derivatives.
Yeah.
We're actually implementing this now, and we're looking at this.
Yeah.
But yeah, so here we haven't done this. Also, we want to look at sort of how the Ricci tensor evolves. So this is, we only know that if the Monge-Pay equation is solved, then Calabi-Yau theorem tells us that the metric is Ricci flat, but it could get less Ricci flat in between and become more Ricci flat again. So for this implementation, we haven't done it.
Actually, Fabian, let me comment maybe.
Can I say one
yeah.
You can compute the Ricci tensor more easily if you use a fixed Kähler potential. That was what Damian was asking. You can write down a fixed Kähler potential in the ambient space up to some certain degree, and then restrict this. And for this, because you can just sort of algebraically compute the derivatives, in this case, you can actually compute the Ricci tensor more easily. And in this case, we do have a guarantee by Donaldson's algorithm, for example, that the Ricci tensor is getting smaller and smaller. If you do this with the metrics directly, I mean, learning the metric directly, you don't have this guarantee, and this will tell you sort of the fact whether Ricci flow or whether the Ricci tensor flows to zero, whether it has some bumps in between. This will tell you something about the loss landscape. Or in other words, if you're close to satisfying a Monge-Pay equation, how close are you actually to a Ricci flat manifold?
Yeah.
Yeah, so as a comment, so in the sense for the metrics that come from some Kähler potential that we looked at, we actually implemented the Ricci tensor also as a loss, as a potential. And there we see that it's going down. Yeah, so in some sense it's following that. But Fabian mentioned this, I guess, as well. But so in that sense there.
If it comes from a Kähler potential, you can compute it algebraically, the derivatives. That's easier.
No, but they are also calculated via auto differentiation. So it also is calculated directly.
Yeah, sure, but it's sort of, it has some built-in polynomial smoothness thing.
Sure.
That's very interesting. Thanks.
A question that's kind of related to David's, which is being sort of away from the right metric, is you know, in some of these have you thought much about these singular cases where you can't get rid of the singularities? You know, like these Q factorial terminal singularities, for instance. And I mean, to me, it seems that there's sort of a natural question, which is if you got close to the Ricci flat metric and you considered fluctuations away, but you know from math that you simply cannot deviate. You cannot resolve the singularity in a way consistent with Ricci flatness, with a smooth Ricci flat manifold. I mean, in principle, the minimal loss that you can achieve in those contexts presumably could tell you something physical. Have you thought much about these cases in this context?
No, it's an interesting point. So Jim's point is that there are singularities in manifolds that you can resolve correctly. You can resolve it while keeping a Calabi-Yau metric on the space, and in other cases, whatever you do to make the manifold smooth, you would necessarily lose the Calabi-Yau property. So, of course, we are not flowing in moduli space, so we're not doing this resolution in some way. We have a fixed input. This would be a singular space, and then again, presumably, what would be happening is you're learning the metric. And at the singular point, this would have a zero eigenvalue. So if I was sampling points and putting in a point where the Calabi-Yau is singular, I would find zero eigenvalues there. So I'm not entirely sure whether you would learn something. What you could, of course, do is you could run the entire program on, let's say, a sphere or something that doesn't have a Calabi-Yau metric and see that it fails to converge. Or you could try to find, in some sense, the flattest metric you can find on a sphere by optimizing the Ricci loss.
And I guess part of my point is flattest you can contains physical information, right? So if you really had a zero loss exact Ricci flat metric represented as a neural network, then you could move in the moduli space. Well, sometimes you want to study normal directions where there's massive fluctuations, and the minimal loss you got in that context, if you could beat down the systematic so that you really had zero loss for the real thing. I don't know, it's just potentially a way to try to get at some things associated with massive fluctuations.
Yeah. Thank you.
Which is basically impossible otherwise.
Yeah. That's a good point. No, I hadn't thought about this or realized this before.
Could you comment on whether you guys are thinking about G2 stuff and non-BPS stuff in that context?
So far, I've thought about SUN structure. So for G2, I mean, in principle, you can also run this for G2. So for G2, you have the 3 form, the 4 form, and then you could set up a similar problem to SUN structure. You could just set up the G2 structure, and instead of Kähler, you impose whatever the correct relation between the 3 form and the 4 form is to give you a G2 structure. And
right.
Yeah, but nothing relies here on being Kähler or complex or whatever. You can just abandon all of these constraints and replace them by whatever space you want to describe, and then learn the metric that way.
Well, I guess, I mean, in some sense, it's you can totally recycle this technology there, but what it's telling mathematicians is something different, because, you know, in this case, you guys are telling them, here's a numerical approximation to a metric that you know exists, whereas it's really hard to construct G2 metrics generally. And if you could imagine like coming up with some clever way to use this sort of technology to you know, lead to potentially new G2 constructions even.
Yeah, that's right. So of course, in the Calabi-Yau case, we were running this and we knew a solution existed because we did it on a space that satisfies the conditions that went into the Calabi-Yau theorem in the first place. So we knew that the thing will converge and it will find the metric. You could do this on some other space or for some other metrics where you don't know whether they even exist, see that they converge and say, okay, this thing actually was a Calabi-Yau. So that would be the equivalent of not having Calabi-Yau's theorem and just finding a metric that satisfies this equation. And if you can find something, if you can find a metric that satisfies this equation, you know it's a Calabi-Yau space in retrospect.
Yes. Do you allow crazy questions?
Yes, please.
So, I mean, something that would be like the holy grail in G2 geometry is if you could come up with an analog of Yau's theorem. So there's a question here of like, you know, given that we know what the answer is, could you use machine learning to try to, in some sense, guess the Calabi conjecture? So, for instance, if you did this, you could try to do this story that you have doing the stupidest example for every degree on hypersurface in P4, right? And you could study how the degree of that surface affects the ability to minimize the Monge-Ampere loss or something like that. My question is whether you could discover the Calabi conjecture. I mean, it's a pretty natural thing to do, right?
Yes.
Study the minimized Monge-Ampere loss as a function of the degree and hypersurface as a function of n in P4. Anyways, I'm just spitballing a little bit, trying to think of everything that I know that is related to this at all. I mean, in G2 geometry, we know a lot of the different topological things to look at in those contexts. But what we don't know is what set of topological things guarantee the existence of a G2 metric.
That's interesting.
But could you just do this sort of stuff for the case I said, just study the Monge-Ampere loss as a function of n?
Yeah, sure, that's absolutely conceivable. Yeah, you could just say, okay, I don't know that sort of. If I hadn't had the Calabi-Yau theorem, I wouldn't have known that I should write down a equation of degree 5. So I write down an equation of degree 1, 2, 3, 4, 5, 6, 7, and I find that the Monge-Ampere loss goes to 0 precisely when I set this to 5. Yeah, I mean, it would be really like to sort of try as hard as you can at each end with machine learning, and to, you know, see some parabola or something that has a minimum at n equals 5 would be really cool. Yes.
Yeah. Anyways, are there other questions for Fabian?
Yeah, I have a simple question about dimensionality. So naively, you'd expect that learning a metric, or really, I guess, any function over a space of higher and higher dimension would get exponentially harder, just because you have to sample points, like you have to sample an exponentially growing number of points. So, I mean, is that dimensionality a problem for the complexity of the manifold and the dimensionality of this string theory problem?
So the dimensionality, yes. So the dimensionality that would go up is, I mean, the Calabi-Yau is always 6-dimensional. So you're always sampling points from a 6-dimensional space. But if you now don't put this in a complex 4-dimensional space, but in a complex 100-dimensional space, which you can do, then of course sampling these points might be more tricky, but using this construction with the line and so on, you just get the points in Calabi-Yau. So I don't think this is where the problem is coming from. So the curse of dimensionality bites you when you sort of have to have many different coefficients here. So the points in the Calabi-Yau itself, because the Calabi-Yau are 3-dimensional, that's not the problem. The problem is that these other spaces, the position space and the volume space, can become very high dimensional. They are easily 100-dimensional, 1000-dimensional, and then I wouldn't know what to do, because then you would have to sample points from this 1000-dimensional space, and this is completely hopeless, I think.
Okay. So it's like 6 dimensions isn't large in some sense. Like if you had to sample 100 points in each of the 6 directions, then that gives you like a very large number of
or something.
Yeah. So like 6 dimensions is still small as far as this problem goes. Like it's small enough.
Yeah. So we explicitly used 50,000 points in this complex, in this 8-dimensional space, or in this 8-dimensional space that lie on the 6-dimensional Calabi-Yau. So that's what we got for 50,000. We got this 1 order of magnitude decrease. So even though in some sense the points are still sampled sparsely, because as you said, so if I have a 6-dimensional space, having 50,000 points is not a lot of points. So this probably tells you that your manifold is not doing a lot along. So a point is a good representative of a bigger area inside this. And then if your manifold is sort of strongly curved around this, you probably need to sample more points then. But in order to know whether it's curved and where you need to sample, you would need to know the metric in the first place. So yeah, it seems to be doing okay. As I said, if I increase the number of points, if I use, instead of 50,000, I use 100,000, this goes down by a further order of magnitude. So this already tells you that this was not very good, but compared to sort of having no idea what your geometry looks like whatsoever to having sort of found a Ritchie flat metric up to 6% or 5%, this is a huge increase. So depending on how exact you want to get and what you want to do with the metric, knowing an approximation up to this 5%, which this is giving you, might be already good enough.
Thanks.
Any other questions for Fabian?
Just going the other way, you could do K3, right? And then come up with metrics for K3, and it's just a 4-dimensional problem, I suppose. I mean,
yeah, K3 is doable, and K3 is very interesting because recently there have been constructions of doing analytic Calabi-Yau metrics on K3 manifolds using very special properties of K3, so using hyperkähler quotients and so on. So this was done by Kashu and collaborators. It would be interesting to do this for K3 and to compare to their expressions. But what they are doing is not very easy. So this is sort of working this out for one example is already very, very involved. And then we would need to do this and then compare what we are doing. But I agree, it would be a very interesting project to do.
Very cool.
And maybe I also have a small question. Can you hear me?
We can hear you, yeah.
Yeah, good. So if you have a metric, can you some kind of bootstrap it? So to use it to sample more data. So just like on some step, you have some approximation to the metrics, and then you use this metrics to sample more data. Did it make sense or not?
Yes, so you mean that, yeah, so I could sort of take an approximation and then sample my points. So in the beginning, I don't know the metric at all. So when I sample sample my points, I just do it with this method. But the closer I get to knowing the metric, I can do this. So I could resample points at every step because, as I said, generating these points is very simple, and I could use my better and better knowledge of the metric to get away from this problem and more into this more uniform sampling. This is what you're proposing?
Yeah, somehow is it consistent that the samples which you get from your metric, are they consistent with this resampling method? Do you have the same? Can you compare or?
Yes, it's a very good point. So crucially, I'm keeping the volume fixed when I do this in some sense. So my metric I'm changing. So for even every given metric, the volume is fixed and the shape is fixed, and I'm just doing this sampling. If I was to change my volume in the process, then this J here would change. And if I was to change the shape, then this omega would change. So at a given fixed point, sort of this J is fixed and this omega is fixed, and so these weights are fixed. And I'm not changing this. So as long as I keep this fixed, the weights will be the same whether I use the approximate metric, so the Fubini-Study metric here, or I use already my better metric that has been approximated by my Calabi-Yau. The weights won't change in this case. I mean, sorry, I should say, no, sorry, that's not correct. Scratch that, what I said. Yeah, it's incorrect, sorry, scratch that. Your weights will change because they will be, of course, they will all be, I mean, once you found the Calabi-Yau metric, then J cubed is omega squared, so all the weights will be 1 essentially at the Calabi-Yau point. So you could use this to compute the weights, or when you do the resampling, you could use better and better approximations with the weights you have approximated there. Yes, it's a possibility. And in fact, when we train this, we also try to do this, to resample at each epoch, we throw away all the points we have, we generate 50,000 new points, and we recompute the weights. So this is something you can definitely do.
Great, thank you.
Yeah, thanks for the question.
Any other questions for Fabian? Right. In that case, let's thank him one more time. Fabian, it was a wonderful talk. It was great to hear about your work and work of other people who are in the audience as well. We are excited about follow-ups and look to see the dozens of them that will, I'm sure, exist in the next year. So it'll be a lot of fun to see how far these techniques can take us. So thanks a lot, and I will stop recording.
Thank you very much.